we finally get to see an application of algebra. And we're going to look at an application of exponential functions. And a simple application is exponential growth. And the concept of exponential growth is basically you're measuring some population over time. And the idea is you have some initial population here, and as time goes on, the population grows uninhibited over time, leading to exponential growth. Now, we need an equation that represents this behavior. And so the model that we're going to use sometimes is called the Malthusian model. It's the exponential Malthusian model. The exponential growth model, or the Malthusian model, says that P equals P naught. P naught is P with a subscript of 0 times e to the exponent of k times t. And so P is the population, the output of this function, if you will, and t then of course is your time. But let's label some of this and identify what these pieces are. So obviously P is population after time t. These guys are both variables. As t or time changes, the population changes. So these guys are both variables. They're tied together though. If you plug in a population, you can find the time at which you reach that population. Or if you plug in a time, you should be able to find the population at that time. Then we've got P naught. P naught is the initial population, which in this graph would be whatever this y value is right here at that initial time of 0. And then k is a constant indicating the rate of growth, how fast this population is growing. So the bigger the k, the steeper this is. Now, P naught and k are fixed. These are constants, while p and t are variables that are tied together. In your graph, you can see P naught, but you can't see k. So lots of times you may have to use the model to solve for k. Not always. Sometimes it's provided in the model, but sometimes it's not. Let's do a couple examples. All right, we'll do a simple example first just to get you familiar. A population grows according to the model P equals 1.2 times e to the 0.0059 t power. So P equals 1.2 times e raised to the power 0.0059 t, where P is the population. Let's say it's the population in thousands after t years. Okay, so we've got some units here. The population P is measured in thousands, and the time T is measured in years. So that's important to keep in mind. So let's ask a question now. So this will be part A, let's say. What is the population after 20 years. Well, so the question is pretty straightforward. We're provided a time, so we know that the time t is 20, and it's measured in the correct unit of years. If it were not, we'd have to convert it to years. And the question is asking what's the population, so we're trying to find p. So all we have to do is plug t equals 20 into our model. So we get p equals 1.2 times e raised to the power of 0.0059 times 20. And all you have to do is plug that into a calculator. And when I do that, I typed all of this into my nice scientific calculator, just like it's written here, and I got about 1.35. Okay, so now we just have to interpret this. P is population, and it's saying the population is about 1.35. Well, in this problem, population is measured in thousands. So when we say 1.35, we mean it's about 1.35 thousand. Or you could just say 1,350 is the same thing. 1.35 thousand or 1,350. So we can see that when we have a time, we can easily calculate the population using this model. And similarly, we can ask a different kind of question. We could ask, when will the population reach, let's say, 5,000? When will the population reach 5,000? Well, now 5,000 is not a time, it's a population, and it's a p, so it's a p value. And I'm not going to write 5,000 because my population should already be measured in thousands. It's units. So I'm going to think about it as 5 with a unit of 1,000. So I'm going to plug in 5 for p, and when we say when, we're asking for the time. So now we just have to plug in 5 for our population to our model and solve for t. So we have 5 equals 1.2 times e to the 0.0059 t. And unfortunately, this is not as easy as part A because we can't just put this in the calculator. We have to actually do some algebra and solve this exponential equation for the variable t. And luckily, we know how to do that. So the first thing I need to do is get rid of this 1.2. I'm trying to get t by itself. The first thing to do is get rid of the 1.2. So I divide both sides by 1.2. The next thing I have to do is get rid of the e. So I take the natural log of both sides. And on the right side, when we do that, the natural log cancels the e, and all we're left with is 0.0059 t. So last, we need to take both sides of this equation to solve for t. All we have left to do is to divide by the 0.0059. So t will be the natural log over 0.0059. And I'm going to type that into my calculator just as it is. And when I do, I have to round it. I'll say I get about 241.88. And this is a time value. So what that means is it will be about 242, let's say, years, because time is measured in years in this problem. So you can see this population seems to be growing pretty slowly. If we go back and look at the original model, notice that the initial population, that p naught value, is only 1.2 thousand. And it will take like 240 years for that 1.2 thousand to grow to a population of 5,000. All right, so these are a couple basic examples with the model. However, what if the model's not completely given to us? What if we don't know this growth rate K? How do we do this? Well, we need some information. So let's look at another example. Let's say that we know a population grows uninhibited, meaning exponentially. There's no like ceiling on this population growth. The population grows uninhibited from, oh, I don't know, let's say uh, 312 to 843 over 2 years. So part A, determine a model for this growth. Determine a model for this growth. Well, so this is kind of tricky. So we know the model looks like P equals P naught times e to the power of kt, and we have to start plugging things into this. Well, we know that 312 is the population we're starting with, so that's our P naught, our initial population. And then we know that this time of 2 years is connected to this population of 843 because it takes out 2 years to grow to that population, so those go together. And so now we simply plug those values in, and P is 843, P naught is 312, times e to the, well, we don't know the growth rate. It's not provided for, so we don't know K. So I have to leave it as an unknown K in our model. But K is multiplied by T, which is 2. And now we can see when we plug all of that in, the only unknown in this equation is K. So our objective now is to solve for K. And notice that's not going to be the answer to the question, determine a model. But to determine the model, we have to know our two constants, P naught and K, because they don't change. And then the model is going to be based on the variables P and T, so we're going to leave those in there like they are. So we have to know our initial population and our growth rate K. And so we know P naught already, we have to solve for K. So very much like solving for T before, this is solving an exponential equation because the variable is in the exponent. So we divide by 312. So that's going to be gone. Then we have to get rid of the e, so we're going to take a natural log of both sides. And when the 312 and the e are gone, we're left with k times 2. So to finish solving for k, we're going to divide both sides by 2. Now I did all the algebra in my head there. I'm just removing one layer at a time here until k is by itself. And so k is approximately 0.4970 when I round it. And you want to, since k is not usually a large number, you want to have several digits in your k value. You don't want to round this too much. So I usually like to go with 4 digits after my last 0 here. So 4970. All right, now we have our growth rate, but we still need to know the model. So what's our model? Well, to get our model, we need our constants P naught and K, and now we know both of them. So the model says that the population P can be calculated by multiplying our initial population 312 times e to the power of K, which we also now know is 0.4970, times the variable T. And in this case, P is the population. P is the population after time t, but t is measured in years again, so I say after t years, so I understand how the model works. And now you can do things like what we did in the previous example. You could say, what will the population be? What will be the population after 10 years? Right? And I'm not going to work it out, but once you know your model, all you have to do is plug in t for 10 and solve for p. If I gave you a population and asked for a time, you could plug in a p-value and solve for t. And that's all there is to this. Sometimes the k value, the constant k, is not known in your model. Sometimes it is. But you need enough information to solve for it if it's not. And then you can use your model with the constants p naught and k plugged in to solve for either t or p.